Hey, what's up guys, my name is Cherno. Welcome back to my code review series where you guys send me your beautiful code and I take a look at it. So, it's the end of the trilogy. Over the last couple of videos, we've been looking at the same project, a 2D physics engine, but we've been looking at very different parts of it. In the first video, we talked about memory. In the second video, we talked about how to read code that you've never read before. We focused on pretty much everything there is in this project, except for the actual physics engine. And considering this project is a physics engine, I think it's about time for the finale. So today, we're gonna jump in and take a look at the physics part of this project. And I highly recommend you take a look at those first two videos. Also, as always, the link to this code will be in the description below so you guys can take a look at it for yourselves, unless the author decides to delete it or something. Okay, so looking at the project, obviously in this actual physics engine kind of module, this is where everything exists. So let's kind of go through this. I know that this is inspired by that designing a physics engine in 5 minutes video. All the way back in the first episode when we read Stowie's original email to us, he did mention that. So I'm expecting the design is going to be a little bit similar to that. But basically, if we take a look at this API, it can be a little bit difficult to just see exactly where everything is done. So whenever you look at any API, in fact, when you're designing an API as well, I always say this, start with the actual usage of it. So in other words, how are you going to use this API? It's really difficult to just make an API by just starting to write one of these files, right? What you should do is go to a place where you're actually going to use it. So for example, inside this demo balls and cube, we see these solvers being created. We see the world actually being kind of set up over here. And then we call world.step. That shows me what I actually need to create in my API. So for example, I need a step function that takes this in. I need to have a way to update the entities, etc., etc. So from looking at this, what I can kind of see is that inside this run function, which is very important because this is what happens every frame. By the way, I should probably show this to you guys if you haven't seen it from the previous episodes. Why did that open twice? What's this extra window? It's a bit weird. Does that always happen? It does. Why are you opening up an extra window? I didn't notice this last time. What the heck's going on? All right, let's just ignore that. So basically we can click to kind of spawn in these spheres, I was gonna say, but they're circles. And then also we have these guys, which I can't tell if they're colliding. I guess they are colliding with each other. I guess if they're already inside each other, they don't pop out or something, but we have these kind of squares, and yeah, these guys actually do pop out if they're inside each other. So I'm not sure, maybe it's weird because if I drop these two, yeah, they collide properly, so it's a little weird. But anyway, this is the result, basically. I don't know what this additional window is. We could take a look at fixing that later. But I promised we would focus on the physics, so let's get back into it. If we click the mouse buttons, it's also important to see what actually happens. So you can see all we really do is push back entities. So we make a new circle and push it back into this entities list. And then we go through all of them and we update them and we step the world. So the thing is, it's obviously important. Circle, when we create a new circle, we also pass in world, which is a little bit of an interesting design. Why does a circle need to know about the world? Theoretically, this isn't a bad design per se, but it's just implemented in a little bit of a weird way. But anyway, so we call entity has a dynamics world, and then we just set that over here. I was expecting that it would add it into this world, because obviously this world itself should probably... Okay, so this doesn't actually contain any... Okay, collision world, and then that's... Yeah, okay, that contains the actual collision bodies. Okay, so this is kind of the meat of it, this kind of collision world that we have over here, and specifically this header file. Did I not tell you guys about Brilliant, the sponsor of this video? Time flies when you're code reviewing. If you guys haven't heard of Brilliant, Brilliant is an amazing website filled with so many different courses on various STEM topics. And they have one of the best collections of math courses on the entire internet, in my honest opinion. Whether you're just starting your math journey or you're trying to learn the math that you need for 3D rendering, such as vectors and calculus, Brilliant have a huge collection of really engaging and visual courses on all of these topics. They have these great interactive widgets you can play with to actually understand the math on a deeper level, and they'll quiz you, asking you questions every step of the way so that you actually learn and retain this information. The best thing about Brilliant is that you can get started completely for free. Just go to brilliant.org/thecherno, link will be in the description below. Check it out for yourselves. Just go through their courses and see if you like them. And if you do, Brilliant have been nice enough to offer the first 200 of my subscribers 20% off an annual membership. Huge thank you to Brilliant, as always, for sponsoring this video. We have an unordered map of bodies, and we have a vector of solvers. So I'm wondering why. So this is an unordered map, and it's probably mapping from some kind of ID, if I had to guess, to a pointer of collision bodies. And these are just all of the bodies that exist within our collision world. And then I'm guessing that basically by, where are we, over here? By actually clicking, like our mouse button, we will be adding them into, but where does it actually get added into the world? Because it doesn't look like, it has to though, because you can see here that the destructor of entity actually removes it from the world. But what adds it to the world? Okay, so it's each individual entity itself. I wonder why it's set up that way. I guess because maybe the actual type that it adds is different. So you can see that, for example, circle, in case you're lost, because this is getting a little bit confusing potentially. So we push back an entity over here. It's a circle. Circle is an entity, right? But circle also has a constructor, and even though that does call the base constructor over here, and it does do some things to set it up, such as like set the transform for the rigid body, do all of this stuff, right? The actual circle constructor itself also will add itself kind of to the dynamics world. Now it's not really adding itself, it's actually creating a brand new rigid body, I guess, which represents this and adds it into the dynamics world. And then technically speaking, the circle itself is not really part of the dynamics world. It's actually stored inside this like entities vector, which is a vector of unique pointers, a vector of entities. So that's kind of interesting. So add rigid body, we'll add, so here we are creating some kind of new rigid body. Oh, we're not creating a new rigid body. Man, that is so annoying. Okay, this is the worst. I did not know this was a function. I thought this was like the constructor of an object. I thought you were making a new object here, because I thought that rigid body, so rigid body is actually a function. Yeah, this makes more sense now, which returns the rigid body of, I guess, the entity. So this is kind of interesting. So what happens then is we construct a new circle. The first thing that happens is we call the entity constructor, so the base constructor. The base constructor will go ahead and create a new rigid body like this, and then we go ahead and actually add the rigid body back in the circle constructor into the dynamics world. So the existing rigid body, we're not creating a new rigid body here, we're just returning the one that exists in the actual entity. So I'm not sure why this line of code is here. Like, you could have just put this in the base constructor like that, right? So it's because obviously dynamics world is owned by the entity, and so is this, you know, rigid body, which is effectively what's going on here. I guess the only reason why you probably didn't do that, or the only valid reason anyway, is probably because maybe like some other objects, so like box, for example, they do something a little bit different. So this, no, I mean, this also does the exact same line of code, and so does this. Okay, and I think that's all of your shapes. So basically, this should be in the base, is the way I see it. But yeah, I totally thought you were just making a new one, because obviously, like, a rigid body itself here, I mean, you're using pointers for everything, but this is obviously just an object over here, and you could have just, you know, kind of constructed it like this. That's what I thought was going on. But obviously this actually requires a pointer, and then this itself will return that raw pointer from that unique pointer. So it's a little bit messy, to be honest. I think what's going on here is you're taking in a raw pointer here, and you're adding it, you're calling add collision body. There goes my syntax highlighting, thank you. You're adding your collision body, and you're doing bodies insert body ID body, and then that, I'm sure, stores collision body. So so this is interesting because we can kind of talk a little bit about ownership semantics here, which is clearly my favorite thing to talk about, even though I said I'd focus on the physics. This is physics related, guys. This is physics related. The thing that's interesting about this is that we're falling back to using raw pointers, because what we kind of want is kind of like a weak ref, right? I mean, that's what I assume is going on, right? You kind of want to add a rigid body, but you don't want it to be owning exactly, which is already weird, I think, because like when you add a rigid body and it adds in and all this stuff, the rigid body itself, we know we're actually adding to the dynamics world, and then it's getting inserted into this along with its ID, right, into this map. But the question is, does this own the body, or does it not? Meaning, like, should this keep the object alive or should it not? Because obviously the way you've got it set up is that this is kind of like a weak pointer, right? Meaning that, like, it's not going to keep the object alive. I mean, obviously we're talking about unique pointers, not shared pointers. So it's not reference counted. It can't keep it alive even if it was storing like unique pointers, and that maybe wouldn't even make sense. But my point is, like, I guess what I'm trying to say is that whenever you find yourself dealing with pointers, like raw pointers like this, which is usually quite common. It depends what kind of stuff you're working on, but pointers obviously are very, very common. And even though you could theoretically probably like avoid using pointers altogether if you just used like shared pointers for everything and you just never even touched raw pointers are probably going to keep coming up. So whenever you see a raw pointer here, and this is why everyone is so afraid of them, I personally think that's a bit dramatic, but whatever, is because when you see something like this, the kind of intentions or the semantics of this specific, I guess at the end of the day, it's just a block of memory that this is pointing to, are very unclear. Like, for example, we don't know whether or not this bodies is supposed to be the authority that actually frees the memory if it's removed, for example, from this map. Or maybe it's supposed to kind of read only, in the sense that, like, if the object's available, access me. If it's not, then don't. And that's why it's kind of scary, because just by looking at this and just by having all of these kind of raw pointers floating around everywhere, it's very unclear whether or not this kind of collision body object inside my body's map is even going to exist in the first place, right? So here's the thing, like, even though you're using smart pointers, this kind of ties into new and delete. It's basically the same thing, because inside the entity constructor, what are you doing? You're creating the object, but then the circle constructor actually adds it to the map by calling add rigid body. And then the entity destructor, what does it do? It removes it from the map. So you've kind of got a new in the constructor and a delete in the destructor. It's the same thing. Why? Because this rigid body is a unique pointer, which means that obviously if we're in the destructor of entity, entity is about to die. And entity is the thing that is actually holding this rigid body, which is a unique pointer, meaning it's going to die as well. So therefore, we have to remove it from this map, which again, I think is kind of hilarious in a way, because all of the C++ people are all about like, oh yeah, you should never, you know, create a new entity on the heap by calling new, that's banned. Or why? Because you have to call delete and you might miss that, and that's like a memory leak. Well, the same thing is happening here. We're adding a collision body here and we're removing a collision body here. And if we forget to remove it, we're not technically leaking memory, but what are we doing? We're storing a pointer to memory that has already been freed. And if we try and access that, we'll crash. So arguably, it's actually even worse than a memory leak. Having an invalid pointer is probably more dangerous than simply leaking memory. So yeah, just something to think about. Now, if you want a solution to this, like, to be honest, I can't say that there's a straightforward solution to this that doesn't actually affect the way your code works. But it is possible technically, and this would introduce a little bit of overhead and probably isn't what you want, but just as an example, what you could do is you could kind of promote this to be a shared pointer. And the advantage of that is that because shared pointers are little bit more complicated in their implementation, it means that you can do some extra things with them, such as storing a weak pointer. And this is a completely different story. The only real disadvantage of this, apart from, again, the fact that it's obviously a reference counted system, it's going to atomically increment and decrement, there's going to be a little bit of performance overhead to that. Semantically, the difference is that now this is not the be-all end-all owning object of this specific rigid body. It can technically be shared. However, if you don't share it, what this does enable you to do is have a weak pointer here, which is a non-owning reference, meaning that whilst this map does actually contain a body, what you can do is every time you're about to use it and potentially dereference memory that may have been freed, you can ask the weak pointer, hey, are you a valid object? If not, remove it from the body's map. If yes, then proceed. Now, is this something I would do for this system? Probably not. Even though it might seem like I'm critical of just using a raw pointer here, I'm not exactly. I just kind of wanted to discuss like what you need to be aware of when you do write code like this, because it might not be even something you think about if you don't have much experience, but it should be something you think about. Like memory and ownership semantics, fortunately, unfortunately, depending on if you enjoy it or not, are just a fundamental part of programming in C++. I'm banning myself from talking about anything else other than the physics. Let's actually take a look at how you resolve collisions and all of that. So if we go back into So we're in collision world. I mean, solve collisions, right? I know from looking at collision world that you actually have, it looks like you've separated your bodies and your solvers. That's good. It's always good to kind of separate these things, because at the end of the day, what are collision bodies? They're just like, they store our data. They're just basically buffers of memory that tell us, like, okay, where is the body? What is its size? What is its shape? Like, what are the other physics parameters of it, such as like the restitution, the bounciness, friction, whatever, all of those kind of parameters. It's basically just data only. And then what are solvers? They're kind of our actual systems. So if you look at this from like an entity component system point of view, right, this is kind of like the component and this is the system. And then of course, the entity is like what holds them together, I guess. So this kind of separation is always good. So if we go back into collision world, solve collisions, what happens? So this actually iterates over all of the solvers and it solves all of the collisions that are given to it. So let's kind of see where solve collisions is actually called from. So resolve collisions calls it, and then where's that coming from? Dynamics world step. Okay, so we're kind of back to our main kind of file, which is our application loop. So that calls world step. World step applies gravity, resolves collisions, and move bodies. So let's kind of go through this and see what's up. So apply gravity, first of all, will iterate through all of the bodies that we have in our world, and it will simply apply a gravity force to it. Very simple. We have gravity force. We multiply that with the mass, we create a force, and then we apply force, which I'm guessing is as simple as just doing force plus equals added force. All very simple. And then next step is to resolve collisions. We have a vector of collisions that have been detected. Vector for collisions that have been caused by trigger colliders. Okay, cool. We support triggers as well. That's nice. Update the grid and find the object that can collide together. So what is... Update the grid. Oh, okay. Broad face grid. Right. So we even have some kind of like partitioning system here to make sure that we're not just trying to collide every single object with every single object in our scene. So what I mean by that is, for example, if we take a look at this, if we're trying to figure out the collision for this circle, why would we test it against this? Like, could you imagine focusing on this circle because that's the guy I'm currently like resolving, right? And then iterating through every single object in this entire world, trying to see if they collide. Like, isn't that just a complete waste of time? Instead, what we can do is create like a partitioning system where we basically can, like, okay, there's many ways to do this, but let me just crudely explain one way. So what we could do is basically create something like a grid, right? It doesn't even have to be a quad tree. It doesn't have to be anything like fancy. We can just create a grid. So here's our little grid. What does this do? It literally just divides the world into cells. And what's the advantage of this, you say? Well, if we're specifically focusing on this particular object here, what do we know? We know that it can really only collide with objects inside its own cell. There's no way you can collide with something over here. But what if it's this object, you say? Isn't this object in between like both of these cells? Yes. So what you can do is you can actually expand it, and again, just like for a naive kind of implementation, you could say that, okay, all of the adjacent cells are included as well. Right? Because if you think about it, there's no way you can pick an object here, like even if it's this guy over here that's affecting all of these, there's no way that you can pick this where the center point obviously is technically, I guess, in this cell. There's no way you could pick this and then not include all the adjacent cells and somehow end up with it colliding with something that isn't in this kind of group of cells. Like, that's impossible, right? It will always be just these. So you can see how much this narrows it down. Like, it's important to partition your world and have some kind of spatial partitioning system would be like the correct term for that. This is used a lot everywhere. It's used a lot in 3D games, it's used a lot in 2D games, and obviously not just games, I'm using games as an example, but just in like rendering in general, or like physics simulations. There's so many uses for this, even just dealing with large data sets, because the more you narrow the code down, the more you can avoid doing kind of expensive math to check like the way that all of this collision is actually happening. Now, of course, spatial partitioning systems could be a little bit more advanced than this. Like, we could go into something called a quad tree, which is where what we have is kind of narrowing down of cells. So in other words, you kind of have this situation where instead of just being a flat grid of cells like this, you start off, I'm going to draw this in blue, you start off by just having this kind of quad tree where you just have one of 4 kind of cells here instead of just having like a, a kind of even uniform distribution of cells across the whole world. And then you just ask yourself, okay, well, which cell is this guy in? Oh, it's in this top left one. Cool. So what I'm going to do is now divide this into like 4 cells. And then again, I'll ask myself, where are you? Oh, you're in this one here. Cool. Let me divide this into 4, and so on and so forth. And see, clearly you're kind of narrowing down exactly where in the world this guy is and what other entities are also in that kind of space. But anyway, my point through all of this is just to mention that when we do have a setup like this and you are dealing with a lot of objects, it's really important to be able to kind of minimize the amount of math that you're doing between them, because that's going to be a major bottleneck. And that's what this broad face grid is probably doing. There's actually a lot of comments here which I really like. So a grid in which the physical objects are placed in. This is used to optimize performance by only checking collision colliders that are in the same cell. Okay, yeah, I mean pretty basic. I'm not a genius or anything. It's just that this is a very common concept, of course. It also looks like this class is pretty generic in the sense that you can just specify like any kind of min and max as well as a cell size, and I guess it will just kind of create that. In fact, if we just take a look at where this is actually coming from. So here's broad face grid. So this is actually owned by the collision world, which we would expect. And we update the grid and find the objects that can collide together. So grid.update bodies, and then I'm guessing bodies is, okay, so we have bodies is like a const vector here, but what this will do is clear resize and then go through, and let's see, so we're going to go through all of the bodies. Find all of this stuff. Yeah, okay, we'll ignore it if it's outside of the grid, of course. And then otherwise, it looks like what we're doing here is just creating a bounding box. So this is like an ABB of the actual body, meaning like if we have a circle, we'll get like the bounds of it, which would technically be, of course, very kind of tightly around it like this, right? And so basically x body min and max, this is like your x min, your x max, and then your y min and your y max, or possibly the other way around. And then I guess what we do is just sort them out into their actual cells, which is a vector of vectors of collision bodies. Oof. Okay, I'm glad you're doing the resize, first of all. It doesn't look like you're doing... Okay, yeah, and then you resize the actual specific grid. So we kind of... The way it's arranged, it looks like, because this says grid column, meaning that we, like grid X, we get the specific column. So it looks like we have basically a bunch of columns like this. This is kind of what the outer vector is. And then once we're inside a specific one, that's us being like, say, inside this guy, now it's divided into, I guess, specific cells. And then each of these cells, of course, will contain another kind of vector with all of the actual bodies inside it. That's why this is a vector of vectors, because this kind of outer vector is the specific column, and then the inner vector is the bodies within that cell. And then we'll go through all of those and I guess push them back into a specific grid cell inside that column. So we're just kind of going through and actually creating the spatial partitioning system. And I guess we're doing that every single frame, which is, I mean, in a way it's unavoidable. There are definitely better ways to do this than just brute forcing kind of your way through everything and sorting it out into all these buckets every single frame. But it's ultimately not a bad way of doing it. Now, whenever you kind of are faced with this decision, it's always really important to just think about the work that you're doing to replace other work. So what I mean by that is that clearly this grid update has overhead, right? We have to loop through basically every single object in the entire world and sort it out into like a vector of vectors, ultimately. We have our columns, we have our rows, and then we have the bodies within each cell, right? That's a lot of stuff to kind of deal with. So by adding this, we're clearly slowing down our performance. However, why are we doing that? It's so that when we actually go through these collision pairs, which we retrieve from the grid, we're able to dramatically decrease this section, right? So this section of code, now, the amount of times we actually iterate through this is going to be way less, which again is supposed to raise our performance. But what is really important to consider is sometimes computers just do not work like you expect them to. Sometimes in your head, you might think, oh, this is so slow. Let me just invent this new system to try and reduce this workload. But I see people doing this so many times without actually even profiling or benchmarking or doing anything that would suggest them measuring whether or not what they expect the computer to do is actually happening. And again, definitely not saying this is a thing here because like, well, we know that all of this is going to be slower probably than partitioning it, but I'm just more using this as an example. Like, it's really important that when you decide to commit to something like this, you actually do a little sample, a little benchmark to see, okay, what is the current performance like? Like, how long is this actually taking? And also, am I sure that the reason it's slow is actually true, right? I haven't just made this up. I haven't just assumed that, oh, well, it's slow because the memory access is slow, or it's slow because the arithmetic kind of math that it has to do is slow. At the end of the day, you're a scientist. You're a computer scientist, and scientists need to run tests. So it's really important that you actually do that, because then when you actually calm down and you implement this and you measure, okay, how much performance have I lost by doing this, right? Then the gain is obviously supposed to be higher. And in many cases, this happens honestly all the time. People will kind of do this immediately. And that's why like premature optimization is the root of all evil. Like, even though I don't 100% agree with that quote just as it stands, because there's so many caveats to that, and also because I think some people just use that as an excuse to write bad code. Like, you shouldn't intentionally write bad code. Like, maybe the reason you're making it slow is because you're just not a good programmer and you're hiding behind the whole premature optimization thing. But my point is, with that quote, if you do decide to optimize without even knowing the baseline, then what happens is I might remove your optimization and it might actually be faster. And that's really embarrassing, right? So just make sure that you're always kind of measuring this and making sure that your assumption is correct. Because I guess my point is, if we look at this, like this is a bunch of overhead. And this, unlike this will actually go through everybody in the entire like world. Well, everybody that I guess is actually inside the grid extents, right? It will go through everything. And the purpose of that is to avoid going through everything here, because when we do that and we actually work out these collisions and triggers and we actually go into solve collisions and we actually go to the solver and we ask it to solve stuff, this is where all of the code is, right? This is where all of the math is. This is where it's potentially going to be really slow. And this specifically is what we are trying to avoid. And the way that these solvers are divided here is we have like the ability to have different solvers, because depending on like the shapes or the collisions, there might be different types. So we have this kind of solver generic class, which just has a solve function with collisions to solve. And then we might have different implementations, such as smooth position solver, which is this guy over here. And then we also have an impulse solver, which is what we were looking at before. So going through this, I mean, this is pretty standard. We have these collisions that we iterate through, body A, body B, and manifold, because collision, you can see, has body A, body B, and manifold. This is a nice little way of pulling those variables out of each actual collision struct. Honestly, like, I probably wouldn't write it this way. I don't really have a reason for this. It's just more of a style thing. I prefer to just kind of have const collision, right, with our little reference here, and then just do collision dot body A and body B. Even though we have this kind of collision prefix here, and it might make the code look a little bit more verbose, it's a little bit more clear about where this is actually coming from. This is very subjective, and this is also totally fine. And if anything, it showcases a nice little trick of pulling stuff out of structs, which I think is cool. Okay, so if body is dynamic, then body A, otherwise null pointer. So if it's not dynamic, then we don't cast it into a rigid body. So this is a way of basically, if it's dynamic, I guess, because collision body is a base class, we're really doing like a cast here, like a dynamic cast, I guess, to convert body A, which is just a collision body, into specifically a rigid body, which is a type of collision body. So this is just a way for us to kind of decide whether or not we want this. Okay, and then we get the velocity. So, I mean, this is a bit weird, because check this out. Like, we've got null pointer potentially, and then, yeah, I mean, even Visual Studio is catching this. So what you need to do is, well, first of all, don't do this, right? But another really good kind of early out here would be if a body like is null, and depending on what you're doing here, because I think you're doing more than just comparing collision pairs, you might be doing that. You could just early out basically by saying if these are both null, then just like continue, because there's nothing else to do here. If one of them is null, then we probably can't collide potentially, but we might still be able to actually simulate the impulse, because I'm assuming that's what we have to do on the one that's not null. So that's why you can't just do kind of or, right? Because it doesn't necessarily mean that's bad, but that's definitely something I would do to not waste my time with the rest of this. The other thing is, though, this is bad though, because if it's not dynamic, then this will crash, right? So this is very bad. Going through the rest of this though, okay, we do a little dot product velocity along normal, blah, blah, blah. Here's the actual impulse, and then we have if a body, okay, so here we actually do check for that being false and not. So what is this used for, this velocity? Just to get the relative velocity, and then we apply that. And then, but relative velocity is used here. So yeah, this is very bad news bears. You need to fix that. But then over here, we actually do check to see if it's null. And I guess if it's not null, we check to see if it's kinematic. So that's an interesting way of doing it, because I guess if a body is not null, then a body kinematic. I would have just written this as basically that, It's a little bit shorter. So you're basically making sure that first of all, a body isn't null. So that's the same thing as writing doesn't equal null pointer. But because of course a pointer is a number and 0 is null pointer, we can just kind of treat it as a boolean in the sense that if it's a non-zero number, this will be true. Otherwise, if it's 0 null pointer, it will be false. So we can just check to make sure that that's basically not 0. And if it's not 0, it proceeds to this, which will dereference the pointer and check to see if it's kinematic or not. So that's what I would do here instead of doing this kind of interesting code, which I have to say, I don't think I've ever seen this before. I don't think I've seen someone checking to see if that's not null. Because yeah, I mean, you're doing the same thing here, actually. I don't need to explain this because you're doing the same thing here. You're checking to make sure you're using a pointer kind of as a Boolean expression. But it's just that then you're saying if it's true, do that, otherwise false. Whereas, of course, like that itself will return false and it won't go into this branch. So I would kind of change it to that. And we do friction, just a bunch of fairly simple math, to be completely honest. Check out Brilliant if you're confused. Highly recommend, link in the description below. And yeah, and then we have this kind of situation here as well to actually set the velocity. So here we're actually applying the velocity and here we're setting it to whatever that value should be, minus friction times mass. Yeah, pretty straightforward. So that's kind of the code. Again, overall, I like the way you've done the code. Like, I can't really fault it too much. I guess the only thing I would really say here is you are using, like, obviously you've made your own classes, which is fine, I guess, for learning purposes, and you are using like the standard kind of library with like ABS and stuff. I would probably switch to GLM. They have all of these classes and functions, and of course they'll have stuff like ABS, and the benefit there is that there's a lot more kind of potential for performance improvement because GLM can like take advantage of SIMD. It's just a very kind of robust math library. Well, I mean, I don't know if I can say it's robust. We've had a few issues with GLM in Hazel where there were just bugs, but that happens unfortunately everywhere and can certainly happen in your code as well. It generally does a good job. Okay, cool. I think that's pretty much it. I don't really have much else to say in this code base. I think that generally you've done a very good job. Like, this is like, I don't know, should I start giving ratings? I think that overall I'd probably rate this at like, somewhere between 80 and 90%. Right? So about 8 or 9 out of 10. Probably leaning more towards 8. And this rating, of course, is a little bit subjective because it's going to depend on me a lot. But like the code itself and the way that you've like laid it out, the way you've named things, the way that you've written like comments in these places, is generally good. You've used like unique pointers in the right place. There is some regard to memory, which is good. I don't think there's much regard to memory layout, but that's okay, especially if this is just like a little test project and not something too advanced. I would probably, like, the only advice I'd give is that if you take this project and want to improve it, have a go at playing around with what I said in the first episode of this trilogy with regards to memory. Just test it out for yourself. Try and move things away from necessarily being pointers to discrete kind of separate allocations of heap memory. Try to pull them together into an arena and, or just like even stack allocations, right? Just try and keep that memory more together in one block. Because at the end of the day, what you're doing with physics is you are, in fact, iterating through a whole bunch of just numbers. A whole bunch of numbers, one after the other, and doing math on them. And if they're all kind of loaded up in the CPU cache, ready to be accessed, ready to be, operated upon, that's going to dramatically speed things up. The other thing I would say is that, remember when we talked about the whole grid partitioning system? One other advantage of having this set up is that obviously what it means is that if we are in fact operating on this guy, we can't possibly be touching, this guy over here, right? So these can't collide, which could mean that what you could do is you could kind of take chunks of this and you could actually try and spread it out across different threads and try and run collision detection or response or physics simulation across like different cores, across different threads. And that can also speed it up. It's a little bit challenging to get that to work well. Might not be as simple as it sounds, but I think it's definitely a fun challenge. And multi-threading physics, like, that's always a good idea. I mean, a lot of physics simulations actually run on the GPU, in fact, because at the end of the day, you have all of these kind of discrete points, and even though the kind of detection response thing is a little bit tight, and you can't just, say that I'm going to simulate each one of these guys on a separate GPU core and everything's going to be good. That might work for particles because they don't really collide with each other. Maybe they collide with like a plane or some kind of other like kind of physics, collision, body geometry in the level, but they don't really collide with themselves, so that's easy to do. With this, it's a little bit more challenging, but I think it's well worth the challenge and should be a lot of fun. So let me know if you do all of that stuff. I would love to take a look at this code again sometime in the future with those features. Thank you guys for watching. Hope you guys enjoyed this episode. Don't forget you can send in your code to chernoreview@gmail.com. There'll be some instructions in the description below. Obviously, don't forget to hit the like button if you enjoyed the video. Leave your thoughts in the comment section below as well regarding like if you agree with me, if you disagree, if there's anything else you noticed in the code. And finally, don't forget to check out brilliant.org/thecherno to learn some math, and I will see you guys next time. Goodbye.